Hi, I'm Michael Lawless, Senior Principal Scientist at Simulations Plus. I'll be discussing the Toxicity module in ADMET Predictor in this video. So let's get started. This slide shows all the models in the Toxicity module. We'll first discuss the cardiac toxicity. We have a couple of models that look at hERG channel blocking, and I'll discuss these in more detail in the next few slides. Hepatotoxicity consists of blood level elevation of various enzymes that would indicate liver injury. These models were created based on data partially from an adverse effects government database. The adverse effects are normalized to the number of prescriptions. So for example, if a drug's been heavily prescribed or on the market longer than another drug, it's going to probably have more adverse effects reported. And so these need to be normalized, and they were for these particular models. And then we have, these models are involved in a tox risk called HepX, which I'll discuss towards the end of the presentation. We also have models that look at estrogen and androgen binding to receptors. There are two models. One is a classification model to say, does the compound possibly bind to one of these receptors? And then a quantitative model that's only evaluated if the prediction for the estrogen and androgen receptor binding is positive or is yes. These models are relative binding affinity to the native ligand, and so they're a percentage, going up to 100% potentially. Then we have some models for carcinogenicity. I'll discuss the rat and mouse TD50 and anti-mutagenicity models in more details. We have models for skin and respiratory sensitization. So these are classification models just indicating whether there's a potential for skin and or respiratory or allergic responses. We have several models looking at environmental factors such as fathead minnow, lethal dose, water fleas, etc. These two bottom models are for bioconcentration and biodegradation. So bioconcentration is how much of the compound would go into the fish if the fish was exposed to water with this a particular drug in it. And then biodegradation is a measure of if the compound's a classification model that predicts if the compound would be biodegradable in sewage sludge. Then in the upper left-hand corner, we have kind of models which don't fit some of the other categories. Phospholipidosis, so potentially if the compound would cause phospholipidosis. Maximum recommended tolerated dose. This is a model which we created based on a journal article. And the idea was behind the journal article was that compounds or drugs that are dosed in lower amounts are probably more toxic than those at larger amounts. So we have a particular cutoff. If the compound is predicted to have a dose, recommended tolerated dose below that value, then it could cause toxicity. And then we have developmental and acute rat toxicity models also. This slide discusses our two hERG models. hERG stands for human etheragogo related gene, and it encodes a potassium channel. If this channel is blocked, it can lead to fatal cardiac arrhythmias. So testing for hERG blockage is now mandatory for pharmaceutical discovery and development groups. The first model is a classification model. All of the data is from patch clamp assay, and the cutoff is 10 micromolar. So if the study said that the compound was under 10 micromolar, it would be a positive for the hERG filter. And then also there might be qualitative information. It just says, yeah, this is a hERG binder. So we don't have the quantitative value for that. And then we also have a model that predicts the p-IC50, so negative log of the IC50 value. This is in molar quantities. And then we have contributions to tox risk, which I'll talk about on the last slide. But basically, the Herg filter has to be positive, and then the PIC50, the penalty starts to kick in at 5.5 and is a maximum at 6.0. 6.0 would correspond to 1 micromolar IC50. Okay, next I'll talk about our Ames mutagenicity models. We have 11 models where the model output is either negative, e.g. non-mutagenic, or positive, causes mutagenicity. We have 5 strains of Salmonella: TA98, TA100, TA97 plus 1537. So this is kind of a mixture here, TA1535, and then TA102 plus WP2. And WP2 is performed in E. coli, but essentially give the same readouts for Salmonella. And then each one of these 5 strains, we have predictions with and without metabolic activation. So the ones that are from metabolic activation, the parent compound would be isolated with rat S9 fractions, and then that mixture would be tested in the Ames mutagenicity assay. We also have one model that was built on data from the National Institutes of Health Sciences in Japan, and this comes out of this publication. So Hamna et al. Sent out results from their Ames mutagenicity tests, and people could make predictions on those compounds. These are the statistics for the 11 models. We have the training and test set data here, number total and number correct, then the concordance, so this is the accuracy, and then sensitivity and specificity. And you see that everything's above 70%. But you do see that the sensitivity is typically lower than the specificity. And this is probably because there's a lot more negatives in the data sets than positives. So it tends to be skew the statistics towards higher specificity in there. And then this NIH data set is a very large data set, so 9,000 negatives in the training set alone here. Now, I'll talk about how these different models are combined into a tox risk. What I'll talk about on this slide is called mute risk. So this is a qualitative estimate of the overall mutagenicity. And it works by combining some of the individual models. So for example, from the 11 models, if it produces a positive, that contributes 0.6 to the score. But there are some constraints. TA98 and TA100 are very similar. So if one's positive, the other's typically positive. So for these two, the penalty is only 0.3 each. And then if you want to score a positive for something that's metabolically activated, it only counts if the one for the non-metabolically activated model is negative. So this would indicate that a metabolite was responsible for activating or the positive in that assay. So what we would do is you would take all the scores from or outputs from the various models, give it 0.6 if it's a positive, except for these two. And then, again, only the metabolically activated ones would be a positive. So you wouldn't kind of double count those. And what we do with our risk rules is that we apply all the models to the subset of the World Drug Index, which is about 2,200 compounds. And then we count how many would have a mute risk above 0.1 based on these scores. And that gives about 19%. Typically, we try to get it around 10%. So if you increase the mute risk to 1.2, it would equal 13%. More recently, there was a workshop on genotypic type assays, and they published their proceedings from a working group. So we decided to use the results of that to refine our mute risk model, and we came up with a new risk called mute risk. This is in ADMET Predictor. You'll get both of these outputs in the risk tab. We ended up creating 19 rules here, and then to get the scores for those, we applied our models to a Hansen data set from this publication here. And it's a fairly large curated set of data. We use multiple linear regression to give the kind of the coefficients for the mute risk and come out with a score for each one of those. And I'll show these here in a second here. In our hands, 12.7% of the World Drug Index have a mute risk above 1, 9.5 has a mute risk above 1.2. The next model is the rat_acute model. This is the amount of orally administered chemical in mg per kg required to kill 50% of the rats tested. So typically you'd have several groups of rats. Each group would get a different dose of the compound. You would increase the dose. Then you would determine how many of the rats had died within 24 hours after ingesting the compound. The data sources are the RTEX and ChemID Plus database. The model was built in log space, as you can see from this plot here. And the units were millimole per kilogram. And then we used the model editor to convert the results back into mg per kg. If you look at the global harmonized system, category 1, which is the most severe, the toxicity is less than 5 mg per kg as the cutoff there. The next two models are the mouse and rat carcinogenicity, similar to the lethal dose, except this is a long-term study where you're looking to see if the species, the animal, develops tumors over the lifetime in 50% of the population. So again, you would increase the dose. You'd have several groups. You would increase the dose for each of these groups and then determine if any tumors are produced. And so this is a long-range study. And so a model is very helpful in trying to predict that, because it typically would take a long time to assay the compounds via this test. And we have one for mouse and rats. Again, we use it in millimole. We build a model in millimole and then convert it back to milligram per kg per day. This next slide discusses the tox rules, or tox risk rules. So there are 1, 2, 3, 4, 5, 6 tox risk rules. The first one is the Hard filter, which I mentioned earlier. So if your PIC 50 is between 5.5 and 6, you'll have an incremental penalty or an adjustment to the score. And so essentially for every 0.1 increase in this range, go up 0.2 on the penalty. So the penalty is 0 at 5.5, and at 6 and greater than, it's a 1.0 penalty. For the rat acute toxicity, it is below 200. So here, anything above 300 is not going to be penalized. Between 300 and 200, it's going to have a fractional penalty. And then below 200, you'll have a penalty of 1. XR is the carcinogenicity in chronic rat studies. This one starts at 2.5, or excuse me, it goes down. It's a less than. So anything above 5 is not penalized. Between 5 and 2.5, it's a fractional penalty, and then below 2.5, it's a full penalty. For the mouse TD50, it starts at, the range is between 25 and 40. And then for hepatotoxicity, if the AST and ALT are elevated and the LDH is elevated, so these three are positive, then you would trigger this to get a positive on that. And then the mute risk contributes another point. So if it's above 1, it would be the compound would have a full penalty, and then below 1, it would have no penalty whatsoever. So the maximum penalty for anything would be 6, because there's 6 risk rules. When we apply these to our subset of the World Drug Index, risk is about 2 for 10%. So this would be kind of a cutoff. If your tox risk is above 2, then you want to maybe deprioritize that compound. Now let's look at the toxicity module predictions for N-nitrosomorpholine. We would switch to the toxicity worksheet here. The risks are going to include ADMET risk, CYP risk, absorption risk, and then mute risk, which for this compound is 2.4, and I'll show how that's derived. And then the overall risk is 4.0, and again, I'll show the contributions to that. If we go over to the Ames mutagenicity star plot, almost all the models predict that this compound is going to be a positive, and you would think so because it's got a nitro group in it. But the 97 plus 1537 is a predicted negative, and so is the one where this is metabolically activated. For the Tox star plot, you have the HERG PIC50. This is hatched, so it means the prediction's out of scope for this compound. You have the log of the rat acute toxicity data, the log of the TD50, mouse TD50, and then the 3 blood enzymes that could be elevated that are related to liver toxicity, and then finally the mute risk, which is 2.4. So let's start off at the mute risk first. So if we scroll way to the right, you'll see the mute risk of 2.4. And then here are the codes, 90, 98, 100, 102, 535, and NIH. So if we look at these predictions for mutagenicity, this one's negative in both, so that no penalty applied there. For 98, it's positive in both the parent compound and the metabolites, so you don't double count this, so that would contribute 0.3. Similarly, the TA100 will contribute 0.3. For the 102, both of them are positive. Again, you don't double count this, but this would add 0.6. Similarly, 0.6 for this, and then 0.6 for the NIH. So we've got 3.6s and 2.3s. That would add up to 2.4, which is the penalty here. The mute risk is a little bit lower, but both these are above kind of the cutoffs for the World Drug Index. So you'd be a little worried about these two compounds. Then for tox risk is 4, so we already looked at the mute risk. So the other models are the rat and mouse TD50s and the liver toxicity. So these would add 1 apiece. It's pretty much easy to add these up. But let's look at the HepX first. So it's these last 3 models that start with SEER, LDH, AST, and ALT. All of these are elevated. So again, this would contribute a 1 to the overall score. And then if we look at the TD50s for these compounds, both the mouse and the rat, the cutoff for the rat is below 2.5 would contribute a full penalty. This is 1.0, so it contributes a full penalty. And then for the mouse, the cutoff is 25. So again, that would set off a trigger and set that to 1. The risk code will have a plus sign on it in this example and a minus sign in this example if the prediction is out of scope. So for this one, it's the mouse TD50, and it's got a plus, which means that the mouse TD50 was out of scope, but if the value of the mouse TD50 is below the cutoff, so this would normally have a penalty of 1, but since it's out of scope, what we do is we apply the risk factor, which is in the settings here. So if we go to the ADMET here, the out of scope factor for risk models is 0.5. So it would multiply 0.5 times 1 to give you a value of 0.5 for that particular code. Then for this compound here, the rat TD50 is out of scope. You see it's underlined in red, so that's out of scope. And but it's above the cutoff. So for TD50, for rat TD50, 2.5 to 5, it's above 5. So it normally wouldn't have a penalty, but since it's out of scope, we're going to give it a 0.5 penalty for that particular molecule. Okay, this slide addresses a fractional penalty. So if the predicted value is between the upper and lower bounds, then the contribution is going to be between 0 and 1. So for example, if the risk rule is less than 4 to 6, so anything below 4 gets a full penalty, any above 6 gets no penalty at all, we can compute the equation of the line for points 4, 1. So this is the 4 gets a penalty of 1, and 6 gets a penalty of 0. So the slope of the line is the change in y divided by the change in x. So it'd be 1 minus 0, 4 minus 6, or 0.5 for the slope. And then we can plug in either one of these points into the equation. So we would get y minus 0 equals negative 0.5 times x minus 6. This would reduce to y equals minus 0.5x plus 3. The predicted value is 4.5. The contribution of the risk is going to be negative 4.5 times 4.5 plus 3, or minus 2.25 plus 3, or a risk of 0.75. And, you can kind of tell that 4.5 is closer to 4, so the risk is going to be closer to 1 than to 0. That concludes this video on the toxicity module in ADMET Predictor. This is Michael Lawless, and I'll see you next time. Thank you.